check the chat box for your questions. Okay. For the diagram, okay, I was unsure about where the arrows were. Okay. Okay. The example in the book, within the experiment, in the theory of the experiment, it explains and draws the arrows from hydronium ion side, right? From the H3O plus side, because the hydronium ion has extra hydrogen and a plus charge, so it can actually, is an acid, so it can donate donate proton. So the arrow is coming from H3O plus. You have a H3O plus here, and H3O plus can give electrons, and I'm sorry, it can give H plus to water. Water, the oxygen of the water has two pairs of unshared electron. So you have the electron-rich spot on the oxygen. Your hydrogen, the addition of the hydrogen, it gives positive charge to H3O plus. So H3O plus, it can give H plus, it can donate proton, is acting as acid, it can donate H plus to the oxygen. So how do I know this is H3O? I'm sorry, H3O plus, because H2O has no charge. When you bring a hydrogen, it's going to gain a plus charge. And the solid line, it means that all three hydrogens are attached to this oxygen. When you look at the next oxygen, there are two hydrogens attached, so that is a water molecule. This is a water molecule, that's a water molecule. So the movement of the proton, it can initiate from H3O plus. So proton moves from the hydronium ion or H3O plus to the water, and it can be conducted or continue like a domino effect from, because then this H2O is going to change to H3O plus, is going to end up with an extra plus charge, and the extra hydrogen that can donate to the next and to the next. So it's going to move. When it comes to the diagram that you have on the pre-lab, you have the hydroxide ion here, right? You have the hydroxide ion here, and the hydroxide ion is going to be electron rich. So it's looking for, so it's acting as a base and is looking for hydrogen. So this is a hydrogen acceptor. It's a strong base and it accepts hydrogen. So it takes away hydrogen. So the moving of the hydrogen is going to be from water to the hydroxide. So the arrow, it looks just like the other one. The difference is that in the other one, you started from the part A side, but you had the H3O plus. Here you have the hydroxide on the B. So it's going to move H from the water toward the OH minus. And then this becomes OH minus, and it's going to move one hydrogen from the water to the OH minus. And so the arrows looks just like this example, but the idea is different. So the arrows basically would look exact same, based on the position from the part A to the part B, or from A side to B side, but the idea is different because for the example on the pre-lab, you have OH minus that pulling electrons, pulling the H plus from the water molecule. Okay. From the opposite direction, you mean from the water to, so the arrow shows how hydrogen is moving. Okay, So should the hydrogen move from hydroxide, which is OH minus, to water, or from water to OH minus? Bianca, what do you think? From water to OH minus or from hydroxide to water? Which one has more hydrogen, is capable of donating hydrogen? H2O or OH minus? From water to OH. In the pre-lab is asking you to draw the arrows, right? It's not giving you the answer. It says that you have example in the actual experiment, in the theory of the experiment. What do you think will happen in the pre-lab? So what did you think is going to happen? Which way the hydrogen is going to move? Because it's not talking about moving of electron, it's talking about moving of hydrogen. So which way should it go? I think it makes more sense. Okay, I think it makes more sense that you get from the H2O and the H2O losing H to hydroxide ion. Basically, hydroxide ion is a proton acceptor. Okay. It's just trying to demonstrate the idea, the difference between a proton donor and proton acceptor. Proton donor is a H3O plus, that's acid, is a proton donor, and then the hydroxide is a proton acceptor. If the idea of the Bronsted, Lowry, and Lowry acid base has not been covered in lecture, you might have trouble, but it's a good question. At least the question is a good question, so it makes you think about the definition for acids and base. Don't worry if you have the arrows wrong or right at this point. Try to just look at the definition for the proton donor, like a H3O plus, and a proton acceptor like a OH minus. One is acting as a strong acid, that is the H3O plus, and the other one, OH minus, is the strong base that accepts the protons. Okay. The experiment today. Okay, so as the proton is moving, what happens? It's a good question, so let me explain further. What happens if H2O loses H plus to hydroxide? Is going to gain negative charge, right? So proton is moving from water to the hydroxide. Yes, proton is moving from the water to hydroxide. And then the water, the molecule that originally was water, is going to gain the negative charge. So if you explain that the negative charge is moving from B to A, it's okay. Hydrogens are moving from A to B. Hydrogen is moving toward the hydroxide, but if you explain that negative charge is going to be transferred from the hydroxide to the first water molecule and then to the second water molecule, two-third molecule, that is also correct. So it's just trying to explain what does conductivity means, and if you have like a negative charge, how is going to be transferred within the liquid if it's moving or a mobile phase, like a liquid or aqueous solution, which is a condition for conductivity. So it's trying to demonstrate how the negative charge and positive charge is moving within a solution, like an aqueous solution when you have water molecules available, or if you have a liquid. So it's trying to demonstrate the movement of electrons. As long as you understand that part, the question has served the purpose and the example. So it explains within the experiment, and then it brings as a question and the pre-lab, trying to take your attention back to what you saw before, that charges are moving. Okay, charges are moving within the mobile phase. Mobile phase. It has to be, there must be ions and there must be like a mobile phase. Those are the two conditions, right? And your ions should be mobile in order to be conductor of electricity. Okay, the experiment about ionic and covalent bonding, conductivity of solutions of ionic and covalent compounds. It's going to, we are going to examine a list of different compounds in the solid phase, in aqueous solution phase, in molecular phase as a pure sample or a mixture, and also look at the reactions. We are testing for conductivity of these samples given. I don't know how many of you watched the video already, but the conditions for a compound or substance, not the compound, because if you say it's a compound, it could be just the molecular compound, which is not the conductor of the electricity. But when you say substance, it covers everything. So I correct myself. It's going to be the conductivity of substance. Conditions for that, it must contain ion, right? And the second condition is those ions needs to be mobile. They must be able to move around. If your compound is molecular compound, is not a conductor of electricity. So water, H2O by itself, is not a conductor of electricity. But when it comes to like glucose, is not a conductor of electricity because it's made of only non-metals. It's a combination of non-metals. As a result, it's a molecular compound, and molecular compounds are not conductor of electricity. So we must have ions. And if we have ionic compound, if the ionic compound is solid, again, is not a conductor of electricity. It must be in either liquid form or it must be in the aqueous solution form. So ions must be mobile. Those are the two conditions. And then we have three different class of the compounds that they are conductors. One is strong acids. Strong acids is a conductor of electricity because a strong acid is going to generate H+. And when you say acid, the compound is in the water. So that movement of the hydrogen is going to move the charge also. It is going to cause the solution to be able to transport the charge from one end to the other end in the solution. So one category, because it doesn't specify and it doesn't put numbers, but I want you to add those numbers. One category is going to be strong acids. What's the next category that it's classified as a strong electrolyte? So we have a strong electrolyte, weak electrolyte, and non-electrolyte. Those are the three definitions. A strong electrolyte means that it conducts electricity strongly. Weak electrolyte conducts electricity weakly, and non-electrolyte does not conduct electricity. Now, we want to look at some definitions and see what is strong electrolyte, or what type of compound is predicted to be a strong electrolyte. So when we are testing chemicals, we can predict, is it going to be a strong, weak, or non-electrolyte? Similar to what you answered the questions on the pre-lab. Okay, I already gave you one class, and that is strong acids. What's the next class of the compounds that they are strong electrolytes? Strong bases. Okay, so strong acids. Can you give me examples of strong acids? Sulfuric acid, that's a strong. And Aisha, what's another example for a strong acid? Carmen? Another example for a strong acid? Hydrochloric acid, nitric acid. Okay. There are 6 strong acids, and hydrobromic acid, yes, hydroiodic acid, sulfuric acid, nitric acid, and then you have 3 of them in the group 7: hydrochloric, hydrobromic, hydroiodic. So you have 6 strong acids. You need to memorize those 6 strong acids. And if your compound or the substance is one of those strong acids, it's going to be a strong electrolyte. Now, if you have an acid that is not one of those 6, it's going to be weak acid. So that's how you recognize if it's a strong acid or is not strong acid. The second class you said is a strong base. If the substance is a strong base, it's going to be a strong electrolyte. And Jose, can you give me example of strong base? Jose and Ria, can I get an example of strong base? Lillian? Okay, sodium hydroxide. Lithium hydroxide. So a strong base, it would be hydroxide of anything from anything from group 1A, and couple of the ones from group 2A. So you have a strong base if it's a hydroxide of group 1A. And so it's the metal hydroxide. That's is the base. Okay, if you're talking about like the arenous acid base or arenous acid base, that is a metal hydroxide that releases hydroxide ion in water. So it's going to be a strong base. Ammonia is a base. Ammonia in the base is going to generate ammonium hydroxide when you mix with water. Ammonia is a gas. So when it says like a 5% ammonia or 10% ammonia or 5 molar ammonia, that means ammonia in water. And ammonia in water, it changes as ammonium hydroxide, NH4OH. Yes, except that rubidium is a highly radioactive and it's not in the working condition of the lab. But if you find it, it's going to be very strong base. Yes, that's right. So ammonia is weak base. And in water, as I said, ammonia is gas, but if it says ammonia AQ, that means ammonia in water. It generates ammonium hydroxide, and that classifies as a weak base. Any organic compound that is made of carbon, hydrogen only, and it contains nitrogen, it is going to count basically amines. They are weak bases. Aluminum hydroxide is coming from group 3. Aluminum is from group 3A and is going to be weak base. But if you have one from group 1A or 2A, it's going to be a strong base. You don't have to memorize the numbers, because if you're dealing with like a group 1 or 2 hydroxide, you just classify generally as a strong base. And if it's a group 3, like aluminum hydroxide, weak base. And if it's nitrogen containing compound, as a weak base. So if the compound is a strong acid, is a strong electrolyte. If it's a strong base, is a strong electrolyte. And you need to know the examples. So it's not just definition. So you could answer questions. And then like predict if the substance is given, is it strong electrolyte or not. And the last category would be soluble ionic compounds. So in NaCl is a compound that is ionic. When you add to water, it's going to generate lots of ions. It's going to give Na plus and Cl minus. So your compound must be ionic, must contain ions, and it must be mobile. So when you say NaCl, solid NaCl is not electrolyte, but NaCl in water, because the ions are moving around, is going to be electrolyte. So we have the 3 categories for strong electrolytes. Okay, now Caden, can you give me example of weak electrolyte? What do you think is going to be weak, classified as weak electrolyte? Caden and Caitlin, either one of you. Weak electrolyte? What do you think of weak electrolyte? A class of weak electrolyte. And that is a weak electrolyte because why HF is a weak electrolyte? It's a good example of weak electrolyte, but why would you say it's a weak electrolyte? So if you know the class, then it's going to be easier to recognize it. Acetic acid, that's the example. Again, what class? Why acetic acid is weak electrolyte? It's a weak acid. Weak acid is weak electrolyte, but I don't take the other answer for this question. Molecular compound, if you say molecular compound, if it's not acid, is not going to generate ions. So acids, they look molecular compound, but they are classified already as if you name it acid, it can release proton or is going to generate ions. But if it's not acid, molecular compounds do not generate ions, so they are not electrolyte. So weak acid, if you have a weak acid, is going to be weak electrolyte. Another class, Hannah or Hannah? Kate or Hannah? One of you. So what would be another class? All acid creates ions. Strong acids, they create lots of ions. Weak acid, they create limited number of ions. So weak acids are weak electrolyte because they have some ions. They create some ions, but strong acids, they generate lots of ions, and it's going to be strong electrolytes. Another class, Hannah or Kate? Another class of weak electrolyte. So did you write down which ones are strong electrolyte? What class is a strong electrolyte? Okay, strong electrolytes are the ones, it does help you if you write it down. Strong electrolytes are strong acids, strong base, and soluble ionic compounds, highly soluble ionic compounds. So weak electrolytes would be one class, they already said, is a weak acid. What's the next class? A weak base. Could you give me an example of a weak base? So if it's a weak acid, it's weak electrolyte. Weak base is a weak electrolyte. Could you give me an example of a weak base? I gave a couple examples for weak base earlier. Ammonia is a weak base. What else is a weak base? Ammonia, very good. And any nitrogen containing compound. If the compound contains organic molecules. If it's an organic compound and it contains nitrogen, basically they are known as amines. Amines are weak bases. Aluminum hydroxide also is a weak base. So just keep that in mind. Another class for weak electrolyte. So I'm trying to help you to expand the knowledge. You already know the strong electrolyte. They are a strong base, a strong acid, and highly soluble ionic compound. So if you're looking at the weak, anything that is not strong is going to be weak of those class, right? Weak acid, weak base, and about the ionic compounds, those are the ionic compounds that they are not very soluble in water. They are moderately soluble in water. So if it's moderately soluble, ionic compounds, when they dissolve completely or they dissociate 100%, they are going to generate lots of ions. If they are not highly soluble, if they are like moderately soluble, or if they have slightly soluble, it's going to generate less number of ions. And if you don't have that many ions, it's not going to conduct electricity very well. It's going to conduct the electricity very weak. Last category would be non-electrolyte. What will be peroxide? Peroxide is a molecular compound. Okay, so we're just going to categorize it as a non-electrolyte because it's a molecular compound. If it dissociates, when it decomposes, it gives water and hydrogen, oxygen gas. Both of them are non-electrolyte. Earlier, there was a question, I think, Hannah, that was your question also. And it says about water. Water is not a weak electrolyte. Pure water is a molecular compound, so it's going to be non-electrolyte. So can you give me examples of non-electrolytes? Who has not answered questions? Jada. Carmen, Leah, non-electrolytes. What could be classified as non-electrolytes? You can give me example and then tell me why it's non-electrolyte, or give me the class and say is not electrolyte. Glucose, that's example. Why is non-electrolyte? Because all non-polar gases, okay? So in general, if you say all, very good. These are examples, very good, of the examples. It doesn't dissociate, okay? Sahar, it doesn't dissociate, does not conduct electric current because it does not dissociate. So molecular compounds, they don't generate ions or they don't dissociate. Anything that doesn't generate ions. What about solid ionic compounds? If it's solid ionic compound, also it would be non-electrolyte, because in order to be electrolyte, it has to be able to move around. And if it cannot move around, it's not going to, if it doesn't move around, then it's not going to be able to move the electrons with it. Okay, so that is basically the three class: strong electrolyte, weak electrolyte, and non-electrolyte. In a chemical reaction, sometimes your reactants are electrolyte, the product is not electrolyte, and vice versa. So if you have your reactant non-electrolyte and the product is electrolyte, then you have to experiment it or predict based on the chemical reaction. The simple conductometer that is used in the lab, it looks like this, and we have like two poles that if you place this inside the liquid, if electrons move from one to the other pole, the light bulb is going to turn on. That means the solution that you have, or the compound or the substance you have, is electrolyte, and if not, it's going to be non-electrolyte. If it gives you like a dimmed light, it's going to be weak electrolyte. That's by experiment. But before you experiment it, you can actually predict if it's going to be. Alcohols are not electrolyte, no, because they are molecular compounds. They are not electrolytes. Gatorade is electrolyte because it has lots of soluble ionic compounds in there. So alcohols, actually, they dehydrate. They are not electrolytes. So strong acid, strong base, and soluble ionic compounds. K2SO4AQ, electrolyte or non-electrolyte? Why is electrolyte? If it says AQ, that means it's soluble in water. Okay? If it says AQ, that means it's soluble in water. That compound is ionic. How do we know it's ionic? How do we know that compound is ionic? It's coming from metal and polyatomic ion, or metal and non-metal. And next one is calcium chloride solid. Electrolyte or non-electrolyte? Non-electrolyte because it's not ionic, or is not because it's solid. Because it's solid, very good. Because it's solid, so it is in a solid form. It means that you have the solid calcium chloride. If you place in water, it dissolves. But before you add water, it's solid. And in the solid phase, it doesn't conduct electricity. But if you add to water, it will conduct electricity. Okay. Propyl alcohol. Non-electrolyte because it's a molecular compound. NaF, sodium fluoride, liquid. Sodium fluoride liquid. NaF, sodium fluoride liquid. NaF is ionic compound because it's a metal non-metal, and it's going to be electrolyte because it's in liquid form. So it has to be either in AQ or liquid form. If it says solid, it's not electrolyte. Okay, any questions you might have? Okay, perfect. Okay, let me just look at one. So when you watch the video, you're just going to record your observation in the data sheet that you have. If the light bulb does not turn on at all, then that means that there is no ions, right? So no ions, few ions, many ions. Many ions would be for a strong electrolyte. You get like a bright light. Few ions, that would be weak electrolyte. Actually, I should change this title for the table, and I should make it like a weak electrolyte / few ions, strong electrolyte like many ions, or non-electrolytes with no ions. Tap water is expected to be few ions because tap water has some ions in there, but distilled water has no ions in there. Like if you get the seawater, definitely lots of ion in there. Electrolyte, I mean Gatorade, something, any other, the sport drinks, they have lots of ions in there. But when it comes to distilled ion, it doesn't generate any ions. Or for those of you, had acids and base covered in high school already, know that it's going to give 10 to -7 moles of hydrogen ion. That's a very small number. So it's very, very weak. So now, even without watching the video, you might be able to predict these based on the 3 categories that you have for each one. And then the reactions, let me look at one of these reactions if we have the reactions. Okay. If you mix sodium hydroxide with HCl, what would be the product? Sodium hydroxide plus HCl, what's the product? Or what are the product? Is acid plus base. What do you get as a product? Acid plus base, you would get sodium chloride and water. Very good. Sodium chloride and water. Acid plus base would give you salt and water. So salt is coming from cation from base and anion from the acid. So you get the sodium from sodium hydroxide, Cl from the acid. You get sodium chloride and water. Is HCl electrolyte? Is hydrochloric acid electrolyte? Or in general, reactants are electrolyte or non-electrolyte? Reactants are electrolytes. What about the product? Sodium chloride and water, will it be electrolyte or non-electrolyte? It would be electrolyte because sodium chloride is soluble in water, is highly soluble in water. So both reactants and products is going to be electrolyte. In this example, when you have ammonia, ammonia is a weak electrolyte and acetic acid is a weak electrolyte. But when you get the product, when you get like ammonium acetate is an ionic soluble compound. Your reactants are weak electrolyte, but the product is strong electrolyte. So it's going to explain I will explain it actually while I'm performing the experiment, that you're getting, starting with the 2 weak electrolytes, and that shows that the light is going to be dim light, but the product is going to be strong electrolyte. Okay, if you have any questions, you may ask at this point. If you don't have questions, I'm going to call for attendance and ask you to go ahead and watch the video and pay attention to the reason why these compounds are electrolyte or non-electrolyte, not just writing the observation that it was a bright light or weak dim light or no light, because that's not very scientific. What is scientific is to say why there's so does it generate lots of ions or it doesn't generate ions at all? What type of ions is going to generate? Attendance. Hannah? Sahar? Sonia? Ashley? Leah? Caitlin? Jennifer? Garrett? Carmen? Danielle? Davis? Caden? Sroti? Kate? Bianca? Monisha? Jada? Jose? Sierra? Javier? Lillian? Aisha? Oh, swimming. Javier. Okay, Matthew? And Ria. Thank you. If you have any questions, you may stay, ask your questions. If you don't have questions, you can start watching the video to record your observation and answer the questions. This week, Friday, it's the college professional development date, and I'm gonna have to be, at the meetings. I won't be able to hold office hours this weekend, this Friday. So basically, there are no classes on Friday because of the professional development day. Thank you and have a nice day. So your questions, I have to answer them by email. You're welcome. Yes, Bianca. Did you already do it? Did you resubmit already? Okay, no problem. That's okay. You're welcome. Thank you. You too.